So the talk is about Bitcoin's Asyncio and WebSockets, and I changed the title last minute, and it kind of it's self-explanatory at the end of the talk, not at the beginning. So I won't go into details. So my name is Giovanni. This is my Twitter handle. Born and raised in Italy. Well, somehow I became doctor in theoretical physics here in the Netherlands. Afterwards, I was a PowerPoint wizard at KPMG, or monkey, depending on your point of view. And now I'm a senior shoe designer at Godot Driven. So if you come work for us, I'll design a pair of Nikes for you with the colors of Godot Driven. I'll say it once, maybe, but we're hiring. So drop us a line if you want to work for us. What this talk is about is a side project that I did to experiment with fun new things in Python and Techland. It's something that you can try at home if you don't double with real money. If you do with real money, please, I'm not responsible for any loss you might have. Although, well, we'll see later, but a friend of mine actually made money with a tool that I built, and I'll show you in this presentation. So it's a real thing. How many of you knows what Asyncio is? Yeah, so maybe half of the audience. Basically, it's a new module introduced in Python 3.4 to write single-threaded concurrent code using coroutines. It supports pluggable event loops and ships with one that we will use in this talk. And since Python 3.5, we also gained some new keywords to work with Asyncio, in particular the async and await keywords. Of course, I talk here about an event loop, but what's an event loop? Well, imagine you have a friend, and you're going to give a list of tasks to this single friend. Single as just a single one, not as married or not. And this friend processes the task sequentially. But each task you give to your friend can say, well, do A, and then wait a minute, and then do B. And our friend has the power to do A, and then start with the next task in the queue, which is not B, because we told him, well, wait a minute before doing B. At the end of the minute, B will get picked up, and it will be done by our friend. So basically, we have the illusion that our friend can do things in parallel, while it's not really in parallel. It's just doing other things while he's waiting. But we, as programmers or as users, we have the impression that things happen in parallel or concurrently, because it seems like he's doing multiple things while he was waiting. Of course, our friend is a Python program using Asyncio. That's why I use it instead of they. Of course, it's stupid. Why should we want to wait time between doing A and B? We want it done as soon as possible. But the reality is, of course, that usually when we write our programs, we wait on input-output. So we wait on the database, we wait on the network, we wait on the disk, we wait on other things, and we don't. And the idea behind Asyncio is that we don't have to keep waiting for this thing to be done. We can do other things while we wait for this input-output from these other systems. And of course, you want to see the code. How does it look like? So basically, this is one of the simplest examples that you could do with Asyncio. You import it, and then you write a function which looks almost like a normal Python function, but it has async as before the def to indicate to the interpreter that it's a function that is, well, basically it's a coroutine or a task, a function that plays with our event loop. And then you can use await. Await here is kind of fundamental, because the await part basically cuts the function in two. Because once we reach the await, our event loop will say, okay, now I stop for the right part of the line to be finished before continuing. So basically, you give this function to a friend this friend start to do things up until it finds a wait. At a wait, it stops doing things. It starts doing other things that have nothing to do with this function. And when the right part of the line returns or gives back something, then it will start again. And since here I've wrapped it in a while, basically it goes back to the while, then it continues, and here stops again, waits 1 second, does other things during that 1 second, and then it goes on. So this is the function. And here I kind of create my loop, just like, well, boilerplate. And then the next call is a blocking call, which will return only when my display date coroutine or task is finished. And at the end, I can be polite and close the loop. So if I execute this code, you will see that this is the output. Between one invocation of time and of now and the next one, there's approximately, should be approximately 1 second going on. Yeah, yes. Sorry, I was looking at the millisecond. So indeed it's approximately 1 second between one call and the other one. But of course, it's even more useless because if I just want that, I can just write this function here without no Asyncio, and it basically does exactly the same thing. It waits 1 second. And it print the current time. Well, of course, it's only useful if you have more than one task going on. If you have a single thing and single threaded, then you don't need Asyncio. But let's say I want to do two things concurrently. I want my display date, and I also want to call my hey function. So you can see the hey function. They want to say something, but they can never say it in one go, because the other function, the display date, will disturb him. And so if we run this code here, we'll basically say this. So I first go hey, then there's enough time for the display date to be to emit twice. Then the hey function will go on, and so on. So you can see how these lines here give us the impression that we're doing things in a concurrent way, in a parallel way, but it's doing really concurrently. Well, enough async. Now Bitcoin. What have I done with Bitcoin? So I don't want to offend anyone with Bitcoin or crypto explanations here, but we want to do something fun and get a bot that collects data from Bitcoin exchanges and basically signals when an arbitrage open up. So if you don't know what an arbitrage is, I will explain it more at the end, but basically what we want to do, we want to do market neutral trading, because if you follow a bit of news, Bitcoin is a very unstable currency. And if you own Bitcoin, you're exposing yourself to market risk. So you're exposing yourself to Bitcoin going up and down by maybe also several thousand dollars per day. But we don't want to do that. We don't want to risk our real money. So what we do is that we'll short sell and long buy Bitcoins in the exchanges that opens up and arbitrage possibilities. Again, I will explain the short selling and long buying later, but basically you're not actually selling and buying Bitcoins, but you're selling and buying the risks that Bitcoin fluctuates in price. Later things will be clear. But the core thing is that you do not have a risk on Bitcoin fluctuations. And you can still make money. If you want a longer explanation, either wait the end of the talk, or you can go here to this GitHub issue of Blackbird. There is a number of Bitcoin exchanges that we can poll to see if there is an arbitrage opportunity. So basically, an arbitrage opportunity is that we can buy from one exchange at a low price and sell on another exchange at the same moment for a higher price, and we take the delta minus the transaction costs. The exchanges we can use, well, for example, Kraken, Bitstamp, GDEX, Bitonic, and there are more. But I want to concentrate to two exchanges that offer WebSocket support. So WebSockets, who knows what WebSockets are? Yeah, so even less than Asyncio. Basically, WebSocket is a protocol that enable interaction between the client and the server with low overhead and real-time data transfer in both ways. And of course, this is much better than polling from an API continuously, because if you poll an API, let's say every second, the price could change between one call and the next, so you lose some data there. While if you use WebSockets, the exchange notifies the client if the price change, if there's a trade made, or whatever. And every time you use Jupyter, or Jupyter, as some people say, you're also using WebSockets, because Jupyter uses WebSocket on the background. So, having said that, we could have an architecture that looks like this. We pull from our exchanges. Here I show GDEX and Bitonic, because there are two that offer WebSockets client. We could have our code here, the PyData Async insert, that takes the data, put it into a database, and then we could have an emailer, which I won't talk too much about it here, that looks at Postgres, and every time an arbitrage opens up, it sends an email. WebSockets in our Asyncio are actually a match made in heaven, because if I would look at this code here, like where I make the call, and then I say, well, wait 1 second between this call and the other one, otherwise it will get blacklisted by the exchange or whatnot. I could write this one here, where I just say, well, I'll wait that the WebSockets connection sends me some data. Just wait there. And in the meantime, you can do whatever you want. And once the server sends some data to my program, the program of the event loop kind of wakes up here, and I can continue the execution. So the WebSockets programming model fits very well with the Asyncio programming model. And so, again, while the web server doesn't send anything to my program is free to do other things. For example, to process data from another exchange or do other fancy stuff, or insert into a database. In Python, there's a nice library to work with WebSockets. Of course, it's called WebSockets. There are version 4 already, so it's kind of mature. And we're going to use this here. Oh. How does it work? So this is the hello world example from WebSockets. Basically, instead of connecting to the HTTP protocol, we connect with the WebSocket protocol, and we have an address and a port. And basically, we see here that I just wait from data coming from the server. So here I have WebSocket receive. Then I call greeting, and then I print my greeting. That's my function, and I can run it into my event loop here. Exchanges. So some exchanges also support this protocol, and every exchange has their own way of connecting to it. For example, Bitonic has this following address, secure WebSocket, and then the API, and so on. Then the version, usually version 1. Market, for example, is Bitcoin Euro. And then the channel. The channel could be trades, could be order book, and other kind of stuff. To get data from Bitonic, then, we could say, well, that's my address. I want to connect using the WebSocket. And then while true, so basically just listen forever. Await that the web server sends you something. As soon as you get something, well, basically here I load the message as a dictionary. Then I create a response, which I'll send to the database. And then here I say, well, basically await my insert function. This insert function is the function that sends data into a database. And again, I can use await here as well, because I don't care to be alive while the database is inserting stuff. I could just be set to sleep, and my event loop could do something else. So I just await this insertion. GDEX is a bit more complex, because they want a subscription message before it sends us data. So in this example, we use this subscription message. basically want to subscribe to the Bitcoin Euro channel by listening to the ticker. The ticker is basically all the trades that gets made. And here I had to specify again that I want to listen to Bitcoin Euros. So, since I have to subscribe, that means that I also have to send data through WebSocket. So this one we didn't see. So we can say WebSocket send, and then we send our subscribe message. And once that is done, we just need to send it once. Once that is done, again, we can wait forever and just get data from GDEX. So we await data. The program can do other things while no data comes in. Then some data comes in. We load it into message string. We convert it into a dictionary. We create a GDEX response, and then we insert into our database. Questions up to here? Okay. So where do we store this data? Well, in the diagram I already gave it away. We put it into Postgres. And since we are in async land, and I showed you here that our insert function can work with our async code, that means that I cannot use my favorite Postgres client, which is PsychoPG2. Who knows PsychoPG2? Oh, it's really awesome. But it doesn't work with Asyncio, so I need to use something else. Luckily I didn't have to write it myself, but some nice folks wrote AsyncPG. AsyncPG, as the name says, is a Python async client to work with Postgres. It's developed by a Python core developer and his friend Elvis, which is the guy beyond HDB. That's a website where you can find basically the driver. And how you use it, it's also very simple. You connect to your database, and then you could say, fetch me some values, and close the connection. You can see here that every time there's an await keyword, my function could stop having the focus until the right part of the line has finished. So every time you see a wait here, that means that other function in other part of my code could start doing stuff, which is really nice. Well, in our case, we don't have to write much to insert our data. Basically, we get sent a tick, which is just a trade in our case, which is a name tuple. And I extract the fields from my name tuple, and then I create my query here. It's kind of ugly, and it's worse than PsychoPG2, but that's how the developer said that you should use it. And then here, so this code is synchronous. So my event loop is only doing this one after the other. But once I hit async here, I'm stopping up until I get a connection from the pool. And other people could go on. Then I go to the next line, I stop again because I want to start a transaction. And then in the next line, I wait again for the connection to execute my query. Questions here? Sorry? Oh, well, yeah, sure. It's in the pool. So here I pass a pool object. We'll see it in the code later. But basically the pool object there has all the connection parameters to connect to my Postgres database. So the question was, are the query parameters sanitized before insertion? Yeah, and the answer is that AsyncPG doesn't do it for you, like PsychoPG does. So PsychoPG also allows you to build SQL in a kind of strange way to be super safe, but AsyncPG doesn't do that. But it is kind of fine in the sense that I pass name tuple, which I built myself, and so they're kind of sanitized already uphill. of course, we're almost done. We have all the things in place, but one extra detail is that we're handling time series data. And time series data is kind of peculiar, and Postgres can handle it just fine if you want. But if you want to squeeze performance a bit more, we can use an extension on top of Postgres, which is called timescale. Timescale is an open source extension. An extension in Postgres land means that it's like a plugin. So you don't have to write a different version of Postgres. You can just write the latest and the greatest from the Postgres website and install this plugin. An extension does in Postgres parlance. And it enables not only inserting time series data more efficiently, but also it gives us some extra keywords to make querying time series data more efficient. And yeah, I don't want to go too deep into timescale, but basically, let's say you have a table where TS is a column, which is a timestamp with time zone. Then you can convert this table into a timescale table or hyper table with this piece of SQL here. And so basically here we're saying to timescale, my ticker table as a column named timestamp, and I want that to become my basically my timestamp in my time index. And then at the end I'm going to say optimize it for query which are intraday. This is kind of important, this intraday, this interval 1 day. And why is it important? Because under the hood, timescale will use partitioning. So we'll partition the data into 1 day interval. But it will also do something that usually not all timescale, well, Postgres doesn't do by default, which is it will order data on disk based on timestamp, even when the data does not come in order, which is like what happens when you're inserting data from multiple exchanges, right? So data comes in maybe from GDEX, and there's a particular timestamp, but a couple of seconds later, because the network was slow, data from Bitonic comes in, but you want still them to be ordered. So timescale will reorder the data on disk, and so will make your query much faster. And we will see some performance numbers later. Of course, it's not the end of the world when you spend your query spends 2 days. But of course, if every query asks data for weeks, then it's much better to change your interval here. And the same if your queries are all intra-hour, change your interval to hours, because then it's much more efficient and it's much cheaper to reorder the data by hours. Yes? Well, you could create 2 tables. Yeah, you could create 2 tables, right? Yeah, so that's all. Every table, I mean, the underlying assumption is that every table has kind of a time scale, which is inherent to the table. And if it makes like 3 months and 2 minutes, then maybe you should split them with, I mean, each table should get their own time scale table. Well, these are already set. And they have a cool logo. Also, it's important. So, for example, once we inserted this data into our table, we could say, give me the last ask price ordered by timestamp, which is new. Postgres doesn't have last with 2 arguments. It only has last with 1 argument. Then give me the last bid price, the last timestamp, and then the exchange for my ticker table. And then I want all timestamp between now and 1 minute ago. And I want to group by exchange. So you can see from the results here, yeah, thank you. You can see from the results here that I prepared a talk on the 11th of May, because I got data from 11th of May here. But basically, this kind of, it's already a bit of logic that we can use later. Because now I want to find arbitrage opportunities. I want to find where I can buy low and sell high between exchanges, right? So I could use a previous query, which we just wrote. I call this latest spread. And then afterwards I said, well, let's start from here. Join latest spread with itself in a cross join. So for every line of latest spread, join it with all the other lines of latest spreads. So basically this does a cross join and I get all the exchange possibilities. And then I want the bid price from the exchange when I want to sell minus the S price from where I want to buy should be higher than the transaction costs, which usually are 0.25%, but it could be a parameter. I just hard-coded it here for convenience. Because of course, if this spread is lower than the transaction cost, is of no use. And you could also say transaction cost plus 0.5%, because you want to, I mean, that 0.5% is what you want to keep for yourself. And then, of course, you want the timestamp between the buy from and the sell to be quite close together. Because these exchanges are very liquid. And for example, Bitonic sometimes only sends data, only has a trade every 3 minutes. And GDEX much more often. So if you take the price of GDEX now versus the price of Bitonic 3 minutes ago, everything is scrambled and you cannot make the trade. So you want to limit the interval here. So these are the conditions. And then I want to select the bid minus the ask. I want to, well, basically round the percentage. This is for visualization later. And then I want to know where I should sell and where I should buy. This is already basically all the logic for your emailer. Because the other part would insert data into the database, and then the emailer can just run this query continuously. And if there's something, it could return results. And of course you say, well, it's like kind of a thick query. How is it fast? Well, actually, this kind of runs in 4 milliseconds. And it only needs to, basically it only needs to run on data for a single day. And data for a single day always fits in your RAM. And the nice thing about, well, Postgres and timescale and everything that as the day, I mean, as you go to the next day, you evict the data that was in RAM with the data of today. And so it always remains fast. And of course, 4 milliseconds is fine because the network delay is like 2 orders of magnitude more. Half a second. And this is for a query on a table with 50 million rows, 4 gigabytes of data, and on the smallest and crappiest VM Google offers with a single CPU. So basically, if you go, 5. So if you go higher, you can get much better results. Now show us the real code. Sorry. So let's see. Okay. Well, can you read? No, it was not this. Here. So basically, this is the program that inserts the data. It basically gets all the variables to connect to the database, and then it says, well, if you want to get data from GDEX, use the get GDEX async that we show in the slide. Otherwise, use the get Bitonic async. And we get a pool here. I have to use the mic. So we get a pool here. And then we say, I want to use this pool to insert data into the ticker. And I create my insert ticker async function. And then I just say, well, my dear event loop, please, here, run my get async function, which is either this or this. Once you're done, which is hopefully never, close the event loop, the pool, sorry. And since I want this thing to run continuously, I put it into a while true. So it can kind of continue. It can continue going. And this function here, again, we already saw them. but it is like with logging, which I didn't have in the slides, but it's basically what we already saw. Insert ticker with so, and maybe we can also show the get pool function here. Basically tries to get a connection to the database and get a pool of connection from the database. And it tries 20 times. And the reason is that I'm using Docker. So that means that the image that runs the database is separated from the image that inserts the data. And that also means that while I'm spinning up these images, the database image won't be ready immediately. So the image that inserts the data needs to wait a bit. So that's why I have 20 attempts before getting the pool. Creating a Docker image with this code is very simple. Basically, I get one of the latest Python, and I just add my code, and pip install the packages which are there. And if I want to use it with Docker Compose, I say, well, I want an image from my database, which is the timescale image. And then I want an image to insert Bitonic data and an image to insert GDEX data. And I want them to play together. So let's see if they do play together. Docker Compose up. Can you see? You see I have a lot of exceptions because, of course, we cannot connect to the database. But once the database is ready, like here, then we can see that GDEX, well, Bitonic is still kind of, doesn't have many traits, but GDEX start to connect and to get these messages here. And it kind of goes on and on and on. And I now can connect to the VM where this is running. And you can see here, this is basically the query that I showed you before, a bit tweaked. Oh, I wanted to show you something else. Yeah, so you can see here that, for example, between Bitstamp and Kraken, right now, is like the time in UTC, and we are in UTC +2, so this is right now. There was a spread, which was 8. So this is a spread which is very low, like basically 0, but because otherwise we have to wait like days before a spread opens up. But once this is running, you can see that these are the reports that I get from the emailer. So basically said, well, at this particular time, so 10 days ago, there was a spread between Bitstamp and Bitonic, and it was a spread of 1.45%. So you have 50% transaction cost. That means that you have 0.95% of revenue. Is this real? Well, of course it's real, but do not use this on production. If you want, you can use Blackbird, and Blackbird is a program written in C and C++, which is much more mature, but they still have a thick disclaimer that, I mean, if you use it on with your own money, you're on your own. And then, of course, do not overestimate the amount of money that can be made, because you will destroy the order book if you just want to go, for example, 100 Bitcoins short and long. So let's say we have a spread which is like 80 euros, and 40 euros of our transaction cost. That means for each Bitcoin, we can make 40 euros of revenue. So of course you want to go short and long 100 Bitcoins, short in one exchange and long in the other. And is it possible to do this? I mean, 100 Bitcoins, even at 5,000 euros per Bitcoin, are 500,000, and I don't have 500,000 in the bank. And of course, you need to have it twice, one per exchange. But as I said before, we don't own these Bitcoins. We go short and long on them. So we own the risk of market fluctuations. But since we own the risk on both exchanges and with opposite sides, we own the buy and the sell risk, the risk cancels itself. So we can actually go 100 Bitcoin short and long. But of course, the more we short, the lower the price will get. And the more we long, the higher the price will get. So we need to tickle. So we need to buy very little while the arbitrage is open, and to wait basically that the price gets to its normal value. So I'll show you what this means. So let's say this is like the price is $8,210 if I buy 0.001 Bitcoin. But if I want to buy 97 Bitcoins, the price goes to $8,280. So the price is much higher if I want to buy 97 Bitcoins. On the other hand, if I want to sell 97 Bitcoins, short sell, the price won't be this, but will be 8,175 or something. That means that you are eating your revenue if you buy 97 in one time. So you need to buy a bit, wait that the market stabilizes, buy a bit until the arbitrage is open. Basically, here we want to sell to the red guy, we want to buy from the blue guy because it's expensive, but buying here and selling here, will push the arbitrage close. We'll close the arbitrage. So if you do this, you need to buy very slowly. That was it. Thank you.